Good evening, everybody. Today we'll just go for some more examples of those solid state compounds what we are talking about, that means the spinels. Some remaining examples of these spinels and what are the experimental evidences we can have So, experimental evidences for basically the typical crystal field splitting. That means, whenever a metal center is present and if it can have some immediate environments either tetrahedral or octahedral, and when we talk about these spinels, we can have these oxide anions, and today we will see also the sulfide anions. So, these are the corresponding ligands either oxide or sulfide surrounding the metal ion in a typical tetrahedral geometry or an octahedral geometry. So, whether we can have the corresponding crystal field stabilization and as a result whether we can calculate out the corresponding CFAC values for these systems depending upon the different dn electron configuration. So, they can have different dn electron configurations, and based on that we can have the preferential occupation of the different levels. In case of TD, we can have E level as well as the T2 level, and in case of the corresponding octahedral geometry, we can have the T2G level and the EG level. So, when we calculate out the corresponding stabilization energy, we find that the preferential site occupancy for some of these metal ions in different electronic configurations are there for a typical spinel structure where we have M2O4 type of formula, where M is the corresponding bivalent metal ion and M prime is the trivalent metal ion. So, when we put these bivalent and trivalent metal ions, what we know already that depending upon their different electronic configurations, we can have the corresponding CFAC for these electron configurations in these two geometrical forms. So, when we find that how many number of electrons, unpaired electrons are present, as we know that if it is a copper based spinel, copper 2 plus based, it can be a spinel or it can be a corresponding simple complex such as copper tetraamine complex or copper hexaco complex. So, when it is spinel, we can have the configurations for these two geometries TD and OH geometries. So, we can have the corresponding number of unpaired electrons. Similarly, in case of complexes also, it can be a corresponding square planar complex or it can be a corresponding octahedral complex. So, all these cases will have altogether different number of unpaired electrons. So, we have different numbers of unpaired electrons to the system. So, if we have the unpaired electron, we will see that it can rotate around the positively charged nucleus which is positive, charged. So, this electron can rotate around this positively charged nucleus, and due to its spin contribution as well as its orbital contribution, it can give rise to the corresponding magnetic moment. So, depending upon the number of unpaired electrons present in all this system, we should be able to calculate out theoretically as well as we can experimentally determine the corresponding effective magnetic moment of the system. When we are talking about a system where the individual unpaired electrons, if it is copper 2 plus, we know that is a 3d9 system. So, we have one unpaired electron, and that unpaired electron is responsible for giving rise to the corresponding mu effective value. So, in a magnetically dilute system where this unpaired electron is getting shielded, because this unpaired electron belongs to one particular metal center, and if the copper 2 plus center is there, and we can have either the different oxide ions, sulfide ions, or the simple ligands like ammonia. So, this is the corresponding geometry around the copper 2 ion in a particular complex, where the individual copper centers bearing one unpaired electrons are separated. That means, this molecule is separated enough to the second molecule or the third molecule and so on. So, this particular unpaired electron residing on the single copper center can give rise to a typical paramagnetic center, and it can give rise to the corresponding magnetic moment value due to the presence of one unpaired electron. If they are close enough and they are nearby, then one particular unpaired electron having some moment value can interfere with that of the second electron, and they are basically coupled together, and we are able to see the corresponding magnetic interaction. And there are different types of such magnetic interactions which can control the overall magnetic moment of the system due to some other type of interactions that we will slowly discuss one after another. So, regarding these spinels, what we have seen that we have earlier discussed about the typical aluminum spinels and the iron spinels, where the basic structure is made up of aluminum, and within the aluminum spinel we have the magnesium, and case of iron also the Fe2O4 system we can have, and there we have the other metal centers. Similarly, in case of these chromium spinels, and there are 3 or 4 examples. The first one is very well known due to the presence of it as a mineral system. So, chromite we all know that this chromite is a typical ore for chromium. So, not only it can be processed for chromium extraction, but at the same time it is present within a complex matrix of iron. So, this iron matrix is present, which is the spinel matrix, and this can also be processed for iron as well. So, if the system is such that we can have this chromium iron system, and if the corresponding physical technique is available such that the corresponding percentages of chromium as well as iron can be incorporated in some solid solution, which can be our chromium based alloy. So, that particular physical technique can also be available, where if the corresponding percentages of chromium as well as iron present in the chromium ore matches to that of the corresponding alloy formation, then that procedure can be utilized, as the chromate or as the starting material or the raw material for the corresponding alloy formation. So, like that of our typical spinel structure bearing aluminum, in this particular case also if we can have this chromite structure with that of iron is present with Cr2O4. So, if this is present, so when the chromite is present, so this is Cr2O4 2 minus and iron is present as Fe2 plus. So, this also we can have both iron and chromium, and these iron and chromium can be utilized for in a similar fashion for the corresponding alloy formation. So, next we see that how within this all chromium based spinels we can have other metal ions such as magnesium or zinc. So, when magnesium is present we get the magnesiochromite, because the basic infrastructure for this network is based on chromium and oxygen. So, the network bonding is formed with chromium and oxygen, that means we have the corresponding oxide lattice, and depending upon its normal or inverse spinel structure we can have the entire or the all chromium atoms sitting comfortably within the octahedral sites, or in the inverse structure some of them goes to the tetrahedral sites. Similarly, in case of zincochromite, the zinc is present along with the chromium network, chromium oxygen network. And also we can have the copper present in that particular spinel structure, and we have the corresponding compound as copper Cr2O4. Thus, we know that depending upon the nature of the spinels, the network is forming either from aluminum to giving aluminum spinel, then for iron spinel, and for chromium we get the corresponding chromium spinels. This is one such thing, that means this is the figure typical for the chromite ore what we can get from underground for due to excavation for the chromite ore. So, this can be processed further for utilizing it as mineral. So, this looks like a shiny mineral like structure. So, when iron and chromium mixed oxides we can have, it can be utilized for some catalytic reactions. So, at high temperature this particular compound, this raw material which can also be synthesized artificially in the laboratory, we can prepare this chromite type of material having different texture, different physical morphology and different network or the corresponding powder structures are different compared to that we get from the native environment as the ore, and this can be utilized for a catalyst, and the catalytic reaction is only operating at high temperature. So, one such important example of chromite, use of chromite for water gas shift reaction where carbon monoxide is reacting with water vapor. So, how carbon monoxide could be utilized to react with water vapor for giving us the corresponding carbon dioxide and hydrogen, which is basically the mixture what we get is known as water gas. So, the corresponding water gas shift reaction can show some catalytic activity due to the presence of either chromite or some synthetically prepared, which we can prepare in the laboratory for this sort of material for its catalytic behavior. So, when carbon monoxide is coming, it can quickly interact with the chromium center, because we all know that chromium obviously in its native form, that means in its elemental state, that means in the zero oxidation state, can react with several such carbon monoxide molecule, and when it is reacting in the zero oxidation state, it is giving chromium hexacarbonyl. So, this hexacarbonyl formation gives us some important clue that this chromium center, whether it is in the +2 or +3 oxidation state or the 0 oxidation state, can show some interaction with the carbon monoxide molecule. So, the surface of this chromium, so this chromium surface, so chromium surface can show some affinity for its interaction to the carbon monoxide molecule. So, surface shows some affinity to interact with the carbon monoxide molecules. So, they are showing some kind of interaction, and this interaction is taking place, and we can see that the corresponding water gas shift reaction we can have. So, if this carbon monoxide molecule can react with the chromium center, giving rise to some kind of interaction on the chromium surface, because this iron present, if it is present in the surface, this iron can also show some interaction with the carbon monoxide molecule, because this iron pentacarbonyl type of molecules are also very much stable and well known. So, apart from these interactions for the formation of the hexacarbonyl or the iron pentacarbonyl, we see that carbon monoxide has some good affinity to react with any of these two metal centers. So, as a result, we get a mixture of these two gases when the vapor of water molecules are reacting with carbon monoxide gas, giving rise to the carbon dioxide as well as the hydrogen gas. This is one of the useful technique for utilizing this water gas shift reaction to eliminate the carbon monoxide burden in our atmosphere from automobile exhaust, or in some other cases for environmental point of view. We can take care of these carbon monoxide molecules, and we have plenty of these water vapors available. We can produce in the laboratory also, such that we are able to produce a good fuel gas, which is our hydrogen gas. So, hydrogen gas production can be a very useful technique utilizing these spinel based catalysts. There are some other type of these catalysts can also be utilized for different types of organic transformations at the same time. So, how we can increase the corresponding catalytic function or the catalytic behavior of this spinel type of molecules? If we go for simply changing this metal center, that means this iron center, by some other catalytically more active or catalytically efficient metal center like that of copper. So, one such example is that is not typically a corresponding copper chromite formulation like CuCr2O4, but it has something more. So, is a mixed oxide structure where we can have copper chromite, copper oxide and barium chromate. So, both chromate chromite form is present over there, and this chromate chromite form is coexisting together in the solid state. So, in the solid state structure we have the corresponding formulations for copper chromite, copper oxide and barium chromate. And in organic chemistry, for typical organic chemistry synthesis, we find that this catalyst is very useful for hydrogenation reactions. So, there are some more of these type of spinel molecules which are available for such hydrogenation reactions, including the corresponding hydrogenation reactions followed by ring opening reactions. And such reactions are very much useful in organic synthesis, and people are still working on it to develop new and newer type of such catalysts based on these spinel structures. So, how we can make this copper chromite formulation if it is not available in the native form in nature as a mineral or some ore, we can prepare this particular material for a solution state synthesis in the laboratory or in some point to get some beautiful crystalline form or particular size or particular some nanoparticle type of molecules we can have. We get these as a typical precursor and then corresponding treatment, the heat treatment or something else utilized for the corresponding hydrothermal synthesis. So, in solvent, if the solvent is a typical water, we mix up the individual ingredients, that means the corresponding salts which we require for the synthesis of this copper chromite, including the barium. That means some amount of barium salt, some amount of copper salt and some amount of chromite salt can be utilized. So, we have the precipitation which can be filtered out we get the residue as a solid product, we dry it and then we heat it at a particular temperature, heated at say about 400 or 500 degree centigrade, giving the useful catalyst. So, these are the very simple technique for solution process for the preparation of new and other type of catalyst. So, in this particular case, how we make this barium chromate based copper chromite catalyst is that if we take the solutions of barium nitrate and copper nitrate and a mixture of these two can be added to another solution of ammonium chromate, results in a precipitate which is of different formulation. Say barium nitrate can react to give with ammonium chromate, giving rise to barium chromate, and copper nitrate is also reacting with ammonium chromate, giving rise to some copper chromate formulation, and ammonium ion is there and ammonium nitrate is there basically. So, the presence of ammonium nitrate in the medium basically responsible for the reduction of the precipitated copper chromate at high temperature, say not at 500 degree centigrade, but less than that, which is in the range of 350 to 400 degree centigrade. So, at this particular temperature, the ammonium nitrate which is present over there will be responsible for the reduction of copper chromate to copper chromite. So, is basically some mixed oxides are formed like that of our typical examples what we know for different superconducting oxides, which are also different mixed oxides of say perovskite or any other type of solid state structure. So, these mixed oxides of superconducting type can be formed and it can only result at a particular calcination temperature, because the precipitate, the dried precipitate can be heated at a 350 to 400 degree centigrade for the typical calcination reaction. So, this can also give us some other example of the ruby. So, the naturally occurring ruby material is nothing but is a corundum crystal based on alumina, based on alpha alumina sometimes, that is being doped with some chromium 3 ions, and when chromium 3 ion is doped within the alumina crystal lattice, we see the chromium is occupying some of the holes or the equivalent sites in this particular alumina structure, and the chromium oxygen bonds are getting lengthened, and the chromium in some octahedral environment giving rise to the corresponding characteristic coloration due to the corresponding shape which is determined by the corresponding structure of the corundum. So that basically gives us whether we have some elongated chromium oxygen bond or compressed chromium oxygen bond, and that is responsible for the corresponding DD transitions based on the chromium in +3 oxidation state. And this particular color is not always available, the red color, which is not available all the time, but due to this particular presence of this chromium we can have some other colors also, and these corundum based gems can also be termed as sapphires if the colors are different from the red color of the ruby. So, a red colored artificial ruby may also be achieved by doping chromium 3 into artificial corundum crystals. So, in the laboratory, if the available corundum is not naturally occurring, we can dope artificially chromium 3 into the artificially prepared corundum crystals, and thus we are able to make the corresponding ruby, which can be prepared in the laboratory in a synthetic way, and we call them as the typical procedure for the production of synthetic rubies, because synthetic rubies are very much useful for different optical instruments and for optical properties. So, one such synthetic ruby crystal can be utilized for the generation of laser, which is nothing but light amplification by simulated emission of radiation. So, this laser is basically dependent on the ruby crystals, and these are known as ruby lasers, and it's basically dependent on the stimulated emission. This S is stimulated. S is the stimulated emission of light from the chromium atoms in such a crystal when chromium is trapped within the corundum lattice, and this chromium is responsible for its red coloration due to the typical crystal field which is being exerted on the chromium center in its +3 oxidation state. So, we get the corresponding ruby lasers. So, ruby lasers, its red color is due to the corresponding crystal field stabilization energy within the corresponding crystal lattices of the corundum system. Next, we will see some molecules which belong to the thiospinel group. So, whenever we see that the corresponding magnetite or hematite molecules, we see that there are several such spinel molecules are available where 3 manganese, 3 cobalt or 3 iron centers are there within the O4 oxide lattice structures. So, these structures are there, and all these molecules or systems can have a very strong MO bond, and the nature of this MO bond is it is ionic type. So, all the color and all other things can be very well explained in terms of the corresponding crystal field which we can have, which we can exert on the corresponding metal center due to the presence of these oxides. Now, if we move from these oxide anions to some sulfide anions, because we know that large number of sulfide based ores and minerals are available in nature. Sulfide ores and minerals are there in nature. So, we can have the corresponding sulfur groups, and if we are able to substitute all the oxide pairs by these sulfides, we will have the corresponding formula of these as Fe3S4, Mn3S4 or CO3S4, where we can have the metal sulfur bond, where the sulfur is little bit bigger in size compared to the oxygen atom present in the spinel. So, the nature of these interactions between the metal center and the sulfur is different, and due to the bigger size of sulfur it will be easily polarized, and due to its affinity for polarization and its bigger size, so we can expect that the metal sulfur bonding will have some amount of covalent character, and due to this particular type of covalency which is being generated due to the presence of the bigger sulfur atom attached to the metal, the corresponding interaction between the metal and the sulfur center is not purely ionic, and the corresponding nature of these spinels are little bit different. So, a large number of these thiospinel molecules are available, and we start from cadmoanidite from cadmium indium sulfide. So, we have cadmium cadmoindite. So, we have cadmium is there, indium is there, that is why it is cadmium iron 2s4. So, it is like zinc, and is the cadmium indium is in trivalent state. So, we have one particular arrangement for this within sulfide lattice. Then carolite is copper based on cobalt sulfur network. Then flesterite is the copper, and in the octahedral sites we can have the compositions based on nickel and cobalt. So, it is basically a 3 metal spinel structure. So, 3 metal spinel structures are also there, where this is A site, and within the B site 50% of the B sites are occupied by one metal center and another 50% is occupied by the second metal center. Then greigite, which is Fe3S4, indite is iron indium like cadmium indium. So, indite, so cadmoindite is the substitution of this. So, indite iron is not mentioned, so it is basically iron indium. Thiospinel is known as indine, and kaolinite is the zinc chromium one, lignite is the cobalt sulfur, polydimite is the nickel sulfur. In this particular case, apart from cobalt, this nickel one, the Ni3S4 is a important sulfur spinel structure, because we are now having a thiospinel with a single metal. So, what we have seen earlier, that in case of M prime system, we have M prime 2 S4 system. So, these two are different metal ions, because we can have M as bivalent metal ion and M prime as trivalent metal ion, and this sort of spinel structure are mostly stabilized, and we get large number of these spinels as an examples, where the same metal ion like iron, like cobalt, like manganese can have two possible oxidation states, which are the bivalent ones and the trivalent one, which are stable. But when we talk about the corresponding nickel spinel structure, which is polydimite, so in case of this polydimite, we have this nickel, and since there is no such option for the trivalent metal ion, so in sulfur environment only, which is not possible for the corresponding oxygen environment. So, in sulfur environment, which can show some amount of polarization, that this nickel center is present as both bivalent and trivalent states in tetrasulfur environment. So, in this particular tetravalent tetravalent tetraoxygen environment, which gives rise to the corresponding trivalent nickel, which is not so common and rather unusual. So, this particular trivalent nickel can be stabilized in this particular environment, and spectroscopically we can characterize the presence of this trivalent nickel if we go for electron paramagnetic resonance spectrum, and we get the corresponding signal for the trivalent nickel, which is due to the 3d7 with one unpaired electron, one unpaired electron, and that unpaired electron can very nicely be detected in electron paramagnetic resonance spectrum. So, if this material, if we see that it can show some interesting catalytic activity or any other thing, immediately we can characterize it first for its total nickel content, that means we can determine the percentage of nickel. Then we can find out the corresponding oxidation states, and if it is EPR active for its trivalent nature, we can safely conclude that this particular center can also be catalytically further reactive because of this unusual oxidation state of nickel, and the trivalent nickel in some biological systems also we have seen that this particular trivalent nickel can only be stabilized for some sulfur environment. It can be a thioether sulfur or it can be thiol sulfur. So, in sulfur environment, this nickel can be stabilized in its trivalent state. So, after polydimite we can have sigenite. So, sigenite is again nickel and cobalt present, and depending upon the corresponding oxidation state, if the nickel is in the bivalent state, we have two cobalt centers. So, either one nickel 2 cobalt or 2 nickel 1 cobalt system, if the nickel center can also be supported its trivalent state. Then terrellite is copper and cobalt nickel based selenide. So, like sulfur we can also have the selenide, which is closely related to selenospinel group. So, like thiospinel we can have the selenospinel also because the close similarity between sulfur and selenium. Then violarite, and in this violarite we see that nickel is still present in the trivalent state. So, the sulfur environment is pretty common for stabilizing the nickel in the trivalent state, and iron is present in its bivalent state. So, how we get this Fe3S4, which is greigite structure. So, greigite is the name given for the scientist known as Joseph W. Greig. So, greigite is first reported in recent years by this person who is a mineralogist as well as a physical chemist, who identified this greigite structure. Within this particular case we have the sulfur network and the iron centers are present within this particular environment. So, we have this iron, the red balls are all iron centers and sulfurs are all yellow balls. So, we can have the typical environment for this sulfur. In some cases we see that the sulfur is not tetra-coordinated, it is penta-coordinated, and iron is in a tetrahedral geometry where one sulfur is bound by the four iron centers. So, whenever we find this particular iron, we find that we can have 4 iron centers surrounding this particular iron, and if this particular iron center is there, so this particular iron always can have a tetrahedral geometry, and we can have some other sites which are available as their corresponding octahedral sites. So, we find that how we get all these experimental evidences for crystal field splitting. So far whatever we are talking about is relation to the evidences what we can have due to the corresponding crystal field stabilization. So if we have the splitting, we get a preferential electronic structure, and that electronic structure can give rise to the corresponding crystal field stabilization due to the preferential occupancy in either the T2G or the EG level or E and T2 level in tetrahedral geometry. So what we find that several experimental tools or some theoretical mechanisms can be utilized for identifying the splitting of the 5d orbitals of this T2G and EG levels. So several tools are used to confirm the splitting of the T2G and EG molecular orbitals or the corresponding orbitals which have some participation from the ligand side. That's why we are not considering these T2G and EG levels as pure metal d orbitals, but they are the corresponding orbitals which are formed due to the presence of the ligand orbitals at the same time. So what we get that the corresponding broad range in colors of these transition metal complexes is due to the corresponding electronic transitions. That means if we have one single electron in the T2G level that we have discussed earlier, that the corresponding transition from the T2G to EG level can give rise to the corresponding electronic transition in the UV visible spectra of these complexes. So this can also give rise to the corresponding splitting pattern, and crystal field splitting is therefore operating, then only we have the corresponding DD transitions. So the direct experimental proof for the presence of the crystal field is the observation of the corresponding DD transitions. And lastly, what we will see next, that additional informations we can have by measuring the corresponding magnetic moments of the complexes. So if we have a particular metal complex, say NiL2 or NiL3, and if L2 and L3 are all bidentate ligands, what we will find that we can have two geometries due to the presence of two such ligands and another geometry due to the presence of three such ligands, and we can have the different magnetic properties. Either this NiL2 can be paramagnetic or diamagnetic, and NiL3 can be paramagnetic. So how we can get all these informations? Because we get the corresponding crystal field splitting, depending upon its corresponding crystal field we can have the corresponding high spin as well as low spin electron configurations for these complexes due to the presence of several number of unpaired electrons on these transition metal ions, and due to the presence of these two different levels which can either be the T2G EG, or in some case this can be the ground state for E and this can be the excited state for T2. And if we have several such unpaired electrons, then we can determine its corresponding magnetic moment as its mu effective values. So that gives rise to the information that the crystal field is operating on these all metal complexes. So next we will just talk about the corresponding magnetochemistry, that how the magnetic properties of all these coordination complexes are helpful in determining or identifying the nature of these complexes. So this is basically a characterization technique or characterization tool where we can determine the corresponding magnetism or magnetic properties of all these complexes. So it basically concerned with the magnetic properties of transition metal complexes. So whenever we determine the magnetic properties whether the complex is paramagnetic or diamagnetic in a particular geometry. We will be talking in terms of its corresponding magnetochemistry. And these properties arise from the spin and orbital angular momentum, because we have the spinning motion of the electrons as well as their orbital motion within the orbit, which are present in the complexes, and those motions can give rise to the corresponding moment, and these moments can be found out in terms of its corresponding magnetic moment. So, each electron basically has a moment owing to its two angular momentum values. One is the spin angular momentum, which is basically spinning around its own axis of the electron, and the second one is the orbital angular momentum, where the spinning electron, because of its spin around its own axis, it also rotate around the central nucleus. The nucleus, which is the positively charged part, is present at the very center of this orbit, and due to its typical motion depending upon of its different orbitals, that it can be present in 3D orbitals, it can be present in 4D orbitals or 5D orbitals, and sizes are also different as well as the different orientations for the different levels. We are able to generate the corresponding current and the magnetic field due to the presence of this orbital motion of this electron. And the spin motion of the electron about its own axis also generates a magnetic field. And in the first transition series, where the orbital contribution is not very much, we will talk about the corresponding magnetic moment values in terms of its corresponding spin only values. So, we will be able to determine these magnetic moment values as its spin only values. That is why the spinning motion around the electron in around its own axis is important for developing the corresponding magnetic moment. So, when a magnetic field is applied for a compound or a free ion, a first order Zeeman splitting occurs. So, we can have the different orbitals or the different magnetic levels, and all these magnetic levels can have different energy values depending upon the alignment of all these electrons. So, if we can have two electrons in a particular system, so one electron in one particular orbit and second electron in these two other orbit, and we can have two possible levels or the magnetic levels where we can have these two electrons either paired or unpaired. So, such unpaired electron distributions, this basically gives rise to different types of unpaired electron distribution of these two forms, and these two can have some energy gap which can be considered as delta E due to the different types of these arrangements for this species which are having different number of unpaired electrons. So, these levels basically what we get can be considered as the corresponding Zeeman levels. So, atoms or molecules with spin aligns to the field slightly outnumber the atoms with non-aligned spins. So, more and more number of spins will be aligned to the applied magnetic field to the system. And if we consider the first order Zeeman effect only, the energy difference between these two states is proportional to the applied field strength. So, like that of our crystal field, this corresponding energy gap is dependent on the corresponding field. So, if the field is H, the delta E values for these systems will be proportional to the field strength of the magnet. So, if we have a very strong magnetic field we should be able to generate a corresponding delta E value much more. So, it would be proportional to the applied field strength which we are putting for the determination of the magnetic moment. So, these delta E values basically denoting the energy difference as delta E, and if we can have the Boltzmann distribution, which we all know that a thermally controlled population is dictated by Boltzmann distribution law and K is the Boltzmann constant, then the ratio of these two states or the two populations will be given by e to the power minus delta E by kT, where kT is the thermal energy term, which is the product of Boltzmann constant and T in temperature in kelvins at that particular point. So, with respect to the kT value, we will have the corresponding delta magnitude of these delta E values, and the magnitude of these delta E values are much less compared to these kT values, because the kT values at room temperature would be close to 100 centimeter inverse, but these delta E values are very less. It can only be 1, 2, 3, 5 to 10 centimeter inverse. So, at that particular point when the delta E values are much less compared to kT value, we can consider it as 1 minus delta E by kT value is equal to 1 minus delta E by kT. So, therefore, the susceptibility term, the chi value will be inversely proportional to the temperature. As we increase the temperature, our corresponding chi value will basically decrease with a constant of proportionality, and this constant of proportionality is known as the Curie constant, and this is nothing but the Curie law, and this Curie law is useful to determine the corresponding magnetic moment of all these molecules, and the C value is known as its corresponding Curie constant. And if this temperature can have some correction term, we consider it as the corresponding another T thermal term or T term, which is due to the West constant, and the Curie-Wessels law is also very much useful to show some proportionality with respect to the corresponding susceptibility value. If the susceptibility value is not directly proportional to the temperature, inversely proportional to the temperature, we can go for its corresponding correction term utilizing the West law. So, what we find that when we know the corresponding total spin values of the system, that means S value is equal to the total number of unpaired electron, then we can correlate it to the corresponding magnetic moment as the mu value, which is nothing but twice of S into S plus 1 root mu v. Mu b is nothing but its corresponding value in Bohr magneton, which is a constant term, and mu v is equal to E h by 4 pi m e. M e is the mass of the electron, is equal to 9.274 into 10 to the minus 24 joule per Tesla. So, this particular mu b term is basically gives rise to the calculation where we can calculate the typical number of this unpaired number of electrons. So, if n values are the unpaired electrons, the number of unpaired electrons, and if we substitute S is equal to half of n, because the total S is we are getting due to the contribution of the individual unpaired electrons contributing a spin value equal to half. So, half multiplied by n giving rise to the total S value, and this S value when we put in this equation we get the corresponding mu value. In the same way, instead of putting the S values in the equation, if we directly put the corresponding n values, that means the number of unpaired electrons, which is very easy to find out if we know the corresponding crystal field splitting pattern also, because for the two different types of compounds where we can have the high spin complexes and the low spin complexes, we can have different numbers of electrons. So, for high spin complexes and low spin complexes, which is the direct manifestation of the crystal field splitting, and that splitting gives us different number of unpaired electrons for high spin compounds as well as for the low spin compounds. As a result, we can have these corresponding mu effective values or mu spin only values, because we are considering only the spin only values, the different magnitudes of mu effective values for the high spin complexes as well as low spin complexes. So, next day we will consider all these things, that means all these values, that means the different number of n values for determining the corresponding magnetic moment values for all these complexes. Thank you very much.